Okay, good afternoon, everyone. Recording has started. So today, we're not doing 6.3, we're reviewing. We are reviewing. Okay, so before we start on the review, let me give some announcements first. So I'm having office hours today, and I will still have office hours next week. The only thing that's going to need to change about my office hours next week is because I'm doing the review in this classroom from 1 to 3 on Tuesday, I won't be able to get home for office hours until 3:30. So they'll be 30 minutes later than their normal time. They'll go from 3:30 to 5 instead of 3 to 4:30. So that's office hours. I did reserve this room on Tuesday, April 26th from 1 to 3 for an extra 2-hour review session. So that's 2 hours with me in this classroom, and Daria is having 2 review sessions in the SEC room, right? Mm-hmm. So SEC room in the Russell House from 2 to 4 p.m. on April 30th and on May 1st. And then I'm going to be having office hours next week on Tuesday from 3:30 to 5 and on Thursday from 3 to 4:30 like normal. So, you know, between those you got basically 9 hours of contact time with me or with Daria. And if those review times just really don't work with your schedule, use the Math Tutoring Center. So just Google Math Tutoring Center U of SC. There's graduate students in there from 10 a.m. to 3 p.m. Monday through Friday. So if you are more of a morning studier and you want to go to the Math Tutoring Center at 10 or 11, or you got stuff going on in the afternoon for your other classes, then Math Tutoring Center is a great resource for you. So in addition to that, I have posted to Blackboard under the practice exam folder. I put in the bullet points of all of the things which you should know how to do for the exam. And I've also put a question breakdown of where the questions are coming from, okay? So like certain number of questions from chapter 1, chapter 3, chapter 4, chapter 5, whatever. I haven't posted a practice exam yet, but I will post a practice exam, and when I post that practice exam, probably like at the start of next week, I'll also upload a video solution guide, like how I've done with all the other practice exams. So those are lots and lots of resources for you, but if you are somebody who just needs extra practice problems, I wanted to show you one way that you can do that. If you go to Wiley Plus here and log in, you can go to, if you go to, what do you have to go to? You go to Wiley Course Resources. Yeah, whatever, you can read the book if you want, but there's this tab that says practice, okay? And for every chapter, there's like 10 or 15 practice problems, okay? So if you want to just do some extra problems, this is a good resource for you. Also, the extra problems and things which we didn't get to in the notes are a great thing to practice. So beyond that, you should be able to go back and look at your homework assignments as well. So if you want to go back and study up and you're like, oh, I totally forgot all that stuff that we learned in 2.1 and 2.2, just go to the 2.1 and 2.2 homework. See how you can do those problems. If you can't, that's fine. Just write them down, which ones you don't know how to do, and bring them to one of these sessions with me or with Daria or with a Math Tutoring Center person and get some help for whatever you need help with. Okay, any questions on any of that information about the final exam and studying for the final exam? No? Okay, then we'll start the review for today. Before I start the review, I wanted to do like a couple more examples of this integration stuff from section 6.3. So let me remind us what we were talking about. We were just talking about, well, I know that the fundamental theorem of calculus tells me that if I want to do the integral from a to b of f of x dx, what I need to do is find an antiderivative of that function. So a function capital F whose derivative is little f. And then I just need to plug in b and subtract a. Okay, so the other way that we sometimes wrote this was we would write whatever that function is, okay, and then we'd do a little bar with an a and a b here, okay? So one thing I noticed on the quizzes that I just wanted to clarify was that when we have these a's and these b's here, okay, these are telling us what values x is ranging from, okay? So like on our quiz, we had a question that was like integral from 0 to 1 of v of t dt. Okay, and the question was, let's interpret that. And the answer was that the interpretation of this should be, this is the total distance traveled by the bus, right? But then some people weren't quite sure about how long had the bus been driving. Well, our variable here is t here, and when we put our bounds here, then we are going to accumulate from t equals 0 to t equals 1. So that means if t goes from 0 to 1 and t is measured in hours, then this means that this is going to represent the total distance traveled in 1 hour, okay? So these values on the side of the integral here are x values, and it's where do we start versus stop accumulating area. Okay, so let's do a couple examples here of finding these antiderivatives. I wanted to do a couple more. So let's focus on this one for now. This is part F from 6.3, question 1. So if I want to do this integral, the fundamental theorem of calculus tells me I just need to find an antiderivative for this function and plug in. So who can tell me what is going to be an antiderivative of 2t squared minus 5t plus 1? How about just the first part, 2t squared, a function whose derivative is 2t squared?
2t to the third divided by 3.
Yeah, I raise the power by 1 and I divide by the new power, and the 2 is just going to float along for the ride. How about the next part? A function whose derivative is 5t.
5t squared over 2?
Yeah, we raise the power by 1, so it goes from 1 to 2, and we divide by the new power, which is 2. How about 1, a function whose derivative is 1? Yeah, x, right? Just x. Or t, sorry, thank you. Just t. Okay, so question for the class. Do I need to write plus c?
Yes.
No.
Who says no? Andrew and Christian say no. Can you give an explanation for why?
Because like it's a definite integral.
That's right. We're doing a definite integral here. We have bounds. We're going from 0 to 2. We do not need plus c when we are doing a definite integral. When do we need it? We need it when we're doing an indefinite integral. Okay, so we would need plus c if there was no numbers here, because then we're talking about a family of antiderivatives. Okay, so I don't need plus c, but what I do need is, now that I've found the antiderivative, I take this little integral sign and I change it to be a bar, and I put it on the right-hand side. And all this means, okay, all this notation means is plug 2 and then minus plug 1, okay? Or not plug 1, plug 0. So what do? We plug in 2. So 2 times 8 is 16 over 3 minus 20 over 2 plus 2. That's what I get when I plug in 2. Now I do a minus sign. And now I need to plug in 0, which gives me 0 thirds minus 0 halves plus 0, which is just 0, right? So this is how I do this integration process. We find an antiderivative. Okay, we don't need plus c because it's a definite integral. We have bounds. So we're going to do some plugging here. Okay, so I plug 2 in first, all in parentheses. And now I subtract, and then I plug in 0. Okay, so the top one is what we plug in first. Any questions on this example? Okay, let's see one more example before we go review. Okay, integral from 4 to 9 of 1 over the square root of x dx. Question for the class. When I finish this problem, is my answer going to be a number or a family of functions? It's going to be a number, right? Because this is a definite integral. Okay, this is going to represent the area underneath this function from 4 to 9. Okay, so now I just need to worry about finding an antiderivative of this function, right? And then I'm just going to plug. So do I have any rules that tell me how to do the derivative of something like this? Christian?
Is it the natural log?
What do we think? Should we use the natural log rule to do this antiderivative? Yeah, I think for this particular case, it's not applicable. But when I first started doing calculus, my thought whenever I saw 1 over something was just, well, maybe it's just its antiderivative should just be ln of that something, right? That was my first thought. But it turns out that this is actually only true for 1 over x. The antiderivative of 1 over x is ln of absolute value of x. But for this one, we're going to need to do something more clever. What's the clever way that we've been dealing with square roots all the time when we're doing derivatives? We don't think of them as square roots, we think of them as something else. Yeah, as a 1/2 power, right? So I can rewrite this integral as the integral from 4 to 9 of x to the negative 1/2 power dx. And I have a rule which tells me how to do the antiderivative of x to a number, right? What am I supposed to do when I have x to a number to get the antiderivative? Well, first I gotta...
Bring it down and then put 1 less in the power.
Well, that would be if I was doing a derivative, right? But if I'm doing the...
More of the power.
Yeah, if I'm going to do the antiderivative, I got to swap that process. So instead of multiplying down this power and then decreasing it by 1, I'm going to reverse that process. First, I'm going to increase the power by 1, and I'm going to divide by the new power. So I just make the power 1 bigger than it is, so it goes from negative 1/2 to 1/2, and now I need to divide by the new power, which is 1/2, and I evaluate at 9 and 4, respectively. So I could rewrite this as 2 square root x evaluated at 4 and 9. And then now what I do is, which one do I plug in first, 4 or 9? Yeah, I plug in the top one first. So I get 2 square root 9 minus 2 square root 4, or if you want, 6 minus 2, which is 4. Okay. So on the exam, I just want to be clear about what you're responsible for. We're responsible to know how to do definite integrals and also indefinite integrals of functions of the form, where are they? Oh, they're up here in 6.2, I think. Of functions of the form of these 4 types, okay? So we need to know how to find the antiderivative of a constant, antiderivative of x to a number, antiderivative of 1 over x, that's the special case where we get natural log, and also how to do the antiderivative of e to the kx. So those are the ones that you're going to need to be able to find antiderivative of. Now, if you're doing a definite integral, all you have to do is apply the rule and then plus c, right? But if we're doing a definite integral, so we go from a to b, then we don't write plus c, but we do a bar with b and a, and we plug those numbers in and subtract. Gino?
So if 1 over x is at any power, we cannot use the natural log rule?
You can use the natural log only when the power is 1 in the denominator. If the power is 2 or 1.1 or a fraction or something like that, then we need to use the power rule. Okay, so this power rule really is only applying when n is not equal to -1. If n is equal to -1, then we use this rule. Right? Because if n's -1, then that's just 1 over x, right?
So then if x is in the denominator of s, like the best way to solve it is to do this and then use roots.
Yes, unless it's exactly like 1 over x or 5 over x or something like that. But the power needs to be, the power of x needs to be 1 if we're going to use the natural log. Okay, any other questions on that stuff? Okay, then we can go ahead and open it up to review. So if you brought some questions, then raise your hand. We can work on anything from chapter 1 up until chapter 6. So does anybody have anything that they wanted to talk about or practice? Sure, can we do a velocity problem? Yeah, we can definitely talk about velocity. Let's see if we can find a velocity problem with integrals. That could be fun. Here we go. Okay, so this is problem 5 from, I think, section 6.2. Wait, where did it go? There it is. Okay, so we decide to go on a road trip to Nevada, starting from our home. So on our road trip, we find that our car's velocity is given by the equation v of t equals 2t squared minus 3t plus 8 miles per hour. Okay. So we are supposed to find the function for your position from your home during your trip to Nevada. Okay. So one thing that I want to point out about these velocity problems, okay, is that what is velocity measuring? It is measuring the rate of change of our distance. So if v of t is the rate of change of our distance, then how can I relate the equations v of t and d of t, do you think? What relationship do these two equations, these two functions share?
Time.
Well, yes, time, but they share a special relationship in terms of calculus, right? V of t is the rate of change of d of t, right? So, rate of change, what calculus concept does that bring to mind? Derivative, right? So v of t is the rate of change of d of t, then v of t is equal to d prime of t, right? And so, these two things are going to share a special relationship, right? if I do the following, if I take a function's derivative, right, and I integrate it from a to b, why don't I use a different color? That's too close. If I take a function's derivative and I integrate it from a to b, what do I get? By the fundamental theorem of calculus.
The change from B minus the change at A, right?
Yeah, I get something minus something. What goes in my blanks here?
Capital F of B minus capital F of A.
Right, so when I write little f and capital F in the fundamental theorem of calculus, what I'm saying is that the relationship those two functions have is that little f is the derivative of capital F. So I'm not going to use the letter capital F here because I want to talk about, well, what is the function whose derivative is d prime? That's just d, right? Okay, so this is the fundamental theorem of calculus. Says that if I take a function's derivative and I integrate from a to b, I get the difference in that function from a to b. That's the fundamental theorem of calculus. So this is what I got by putting an integral sign here, dt. So if I integrate from a to b the velocity function, it's the same thing. I get this relationship between the velocity and the distance. Okay, so what does this say? This says that the total change in distance, right, which is what we know this integral to represent, the total change in distance is going to be equal to the location at the end minus the location at the start. Right? So two different ways of measuring. Here's how you can think about it. Integrating a to b of v of t dt is kind of like if I measured the length of my trip by looking at the odometer and watching it go up as I went, right? Well, if I look at the odometer and watch it go up as I'm driving, if I want to calculate the distance of my trip, what do I need to do? I need to check the odometer at the place where I end, subtract whatever was on the odometer when I started. That'll tell me how long the trip was, right? So that's like my d of b minus my d of a. Okay, and it makes sense that the way that the odometer increases has something to do with how fast I'm driving, right? So I take however fast I'm driving, I integrate, which is a way of kind of accumulating our velocity times how long I drove that velocity, right? And then at the end, what do I get? I get the difference in the odometer. Okay, so this is the basic relationship between velocity and distance. So something that is really kind of crucial to know for the final exam is that v of t is equal to d prime of t, where d is the distance function and v is the velocity function, right? The rate at which our distance is changing is exactly to say how fast are we going. Okay, so let's get to the problem now. So that was maybe an aside. Let me add a page. Okay, so keep this in mind as we're doing the problem. So they tell us that that we're going to go on this trip and we're supposed to find the function for our position from home during our trip to Nevada. Okay, I want to modify this problem. I don't like this because we didn't talk about how to do this. I'm going to modify this slightly and ask something more akin to what you might see on the exam, which is find the distance traveled for the first 8 hours of your trip. Okay, so what do they give us? They give us the velocity function. And they're asking us something about distance, right? We know that the derivative of the thing they're asking us about is v, right? So if v of t is the rate of change of my distance, how can I express the distance traveled for the first 8 hours? Plug in v of t into what? Oh, plug 8 in. Okay, question for the class. What do I get if I do v of 8? Who can describe in words? I'm going to get a number. Who can describe in words what this number represents? V of 8.
The number at 8 hours.
What number?
The velocity, first velocity at 8 hours.
This is how fast I am driving at the 8-hour mark. Right? V of 8 is how fast I am driving at the 8-hour mark. Now, this is a little tricky because what is the question asking us for? It's not asking us about how fast we're driving, right? It's asking us about how far I drove. So this is a question not about v, but about d, right? What am I after here? I'm after not v of 8, but d of 8 is what I want. D of 8 is where I am after 8 hours of driving. Now let me ask you a question. Is where I am after 8 hours of driving the same thing as how far I drove? No. What's the difference?
One is mentioning a specific point in time, like how much you drove in that interval, whereas the other is the total amount that the total distance that is driven.
Right. So what does where I am after 8 hours of driving fail to capture? It fails to capture the relevant information of where I was when I started, right? So if I wanted to know what is the total distance that I drove, what would I do? It's going to involve d of 8, right, Christian?
Would you do d of 8 minus d of 0?
That's exactly right. Okay, now if I modify this a little bit, I'm going to do d of 8 minus d of 0. Now this is telling me net change in distance for first 8 hours. Okay, now this is more like what I want, right? Now, okay, let's think about this. What do I want to know? I want to know what this number is. D of 8 minus D of 0, right? But all I have is the velocity function, right? All I have is the velocity function. So let me ask you the following question. Is there a relationship? What relationship does this quantity share with the function d prime of t? Is there a relationship shared by d of 8 minus d of 0 and the derivative of that function d prime? Yeah, this is all reminding us of that fundamental theorem business, right? This is actually equal to what? It's equal to an integral involving this function, right? Okay, so let's write down what it actually is equal to. It's actually equal to what? The integral of d prime of t dt. Are we happy with this statement that these two things are equal to one another? Gino says no. Why not? I'm missing the bounds, right? What does this say? This says that a number is equal to a family of functions. So that's a little bit nonsensical. Let's make it more sensical by, is sensical a word? I guess nonsensical is a word, but let's make it make more sense by adding in our bounds, right? Okay, so what does this say? This says that the net change in distance is given by the integral from 0 to 8 of d prime of t dt. Now I know that the derivative of the distance function is equal to what? This is the same thing as doing the integral of v of t, right? Because v of t is d prime of t. The only reason we use the letter v instead of d prime is just because, well, from physics, we think of how fast we're moving as our velocity. So we use v for velocity, d for distance, right? So I don't want anyone to be confused about what happened here. All I did was I wrote it down in a different way. Okay, so now I think I'm in a good place. How can I proceed from here if I actually want to know what this number is? I don't have a way of figuring out what d of 8 minus d of 0 is, do I? But I do have a way of finding out what the integral from 0 to 8 of v of t dt is, right? Shania?
So we're just taking the derivative of v of t, using that as t?
I think the other way around.
We're using, we're
So the velocity, right, is the rate at which my distance is changing, right? So say I'm measuring my distance from this, I don't know what you call that, podium thing, right? As I'm moving this way, my distance is going up, right? But the rate at which my distance is going up depends on how fast I'm walking, right? So if I was going to measure my distance on a graph, right, as I move forward, my distance from the podium is going up, 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 right? But the speed at which it's going up, i.e. the slope of that function, depends on how fast I'm moving away from the podium. Does that make sense? So in that case, in that sense, the velocity function is the derivative of the distance function. And I know that the distance function has a relationship between the net change in distance and the integral of its derivative. And since I know what the derivative of the distance function is, namely the velocity function, yeah, so now what I need to do is take the antiderivative of this thing. I need to just evaluate what this integral is, right? To evaluate what this integral is, I just need to do the following. I need to integrate 0 to 8 of 2t squared minus 3t plus 8 dt, right? That's what I need to do. So if I can find out what this number is, I'll be done. So who can help me solve this? I need to find an antiderivative of 2t squared minus 3t plus 8. Anyone want to give it a go?
Would be 2t to the fourth divided by 2t to the third divided by 3 minus 3t squared over 2 plus 8t.
And then all evaluated at 0 and 8. Do we agree with this? Okay, yeah, I think I agree with it too. Okay, we want to do the integral from 0 to 8 of this guy. We just take the antiderivative and we move that bar thingy over to the other side. Okay, so all I'm going to do now, you tell me if I'm doing this right. All I'm going to do now is first I'm going to plug in 0 and then I'm going to plug in 8 and subtract. So I would get like 0 minus what I get when I plug in 8. So 2 times 8 cubed over 3 minus 3 times 8 squared over 2 plus 8 times 8. And whatever I get when I do that subtraction is my final answer. We agree? No, I pulled a fast one on us, didn't I? What did I do wrong?
Not include parentheses around the last two terms.
Well, it's not a parenthesis problem.
zeros across.
It's the order problem, right? I plugged in 0 and I subtracted 8. I was supposed to plug in like the following. I should have done this one first and then minus 0. So that was my mistake. Okay, so we should always remember the top one is the one we plug in first. Okay, whoops. I don't know what is happening here. Okay, what just happened? Okay, something horribly wrong has happened here. Okay, this goes over on the other side. -0. Okay, so that is how we would find how far we went. So you just plug in those numbers and see what you get, and whatever that number is the total distance traveled for the first 8 hours. Okay, so this is gonna just be reminding us of something that we learned in section 5.4, which was the following. Let me go back to that. In 5.4, when we were talking about the interpretation of integrals, we said the following. If f of t is a rate of change of a quantity, then the way that we can express the total change in that quantity from t equals a to t equals b is by doing the integral of that function. As long as f of t is a rate of change. Now, what does rate of change make you think of? It's like a derivative, right? So if we integrate the derivative of a function, what do we get? We get the total change in that function from a to b. So if it's a distance function, then we might integrate v of t to get the total change in distance from t equals a to t equals b. Or maybe f of t is measuring the rate at which a drug is leaving my body, right? And then if I integrated from a to b the rate at which the drug is leaving my body, what would I get? The total change in, what's the quantity here? Amount of drug which has left my body. Total change in the amount of drug that has left my body from a to b. Or maybe f of t is measuring the rate at which, I don't know, the rate at which a rocket is on its way to the moon, right? Then we integrate from a to b the rate at which the distance from Earth is increasing. And what are we going to get? We're going to get the total distance from Earth traveled from A to B. So this is about integration and accumulation of change. If we integrate a rate of change, then we get the total change in that quantity. Whatever the rate of change is measuring the rate of change of, right? Yeah.
It sounds a lot like the fundamental theorem in that way.
Yeah, it is the fundamental theorem, right? How can I rewrite total change in that quantity? Well, you could say if f of t is the rate of change of a quantity, how can I interpret that? In other words, what? F of t is equal to f prime of t. That's what it says. F of t is the rate of change of a quantity, f prime of t. Then what is this? This integral is the total change in that quantity, where f, capital F, is the quantity, right? Total change in a capital F quantity from A to B is exactly capital F of B minus capital F of A. It's just a different way of saying the fundamental theorem of calculus. Any questions on that problem? Gino.
Could you just kind of elaborate the significance of little f and capital F and when f has a prime with it?
Sure. So when I write capital F, it's a function whose derivative is little f, right? So capital F of x is, or f of t, is its own function, right? And that function has a rate of change. We can take that function's derivative, right? And I'm saying that capital F is the function such that if I take its derivative, it's little f. So you can think of this statement in two ways. You can say the derivative of capital F is little f, or you can say the antiderivative of little f is capital F. But they have this special relationship. Does that make sense?
So then what about when f has a prime with it? Is that just the derivative of the antiderivative?
Yeah, exactly. That's exactly what this says, right? When I write capital F prime, it's to say that the derivative of this function's antiderivative is itself, right? Because it's equal to little f, right? So yeah, it is kind of weird like that. It's kind of like it's kind of confusing. But yes, this prime just means derivative of, right? So capital F is a function. If you take its derivative, we get little f. Okay, any more questions on that before we move on? Yeah.
Not that, but on the problem we just solved. So I was wondering if the problem was asking about acceleration in that given time, how would we approach it differently?
Okay, so what if the problem was talking about acceleration? Let me ask you the following. Is acceleration a rate of change of a quantity? It is the rate of change. The acceleration measures how quickly what is changing? My velocity, right? It measures how quickly is my speed changing. So if I had an acceleration function, then there's a relationship, okay, between the following functions. The derivative of the distance function measures how fast is the distance changing. That's velocity. But the derivative of the velocity function, i.e. how fast is the velocity changing, is the acceleration. Okay? So if I had a problem that was posed in terms of my acceleration, it might ask me something like, what is the net change in my velocity from time t equals a to time t equals b, right? That's an accumulation of acceleration, right? So in other words, like if I'm slowly depressing the gas pedal, right, over the course of like 3 seconds, you might ask, how much does my speed change? That answer your question? So yeah, all these functions have this relationship. And by the way, what's the relationship between D and A? What relationship does D of t share with A of t? Well, you take the derivative of the distance, you get the velocity. You take the derivative of the velocity, you get the acceleration, right? So the acceleration is the second derivative of the distance, right? Okay, which measures how fast is the rate of change of this substance changing. It's kind of like a tongue twister. Okay, I want to get to more examples before we end class. So does anybody have anything else that we should maybe go find an example for?
Go over problem number, extra problem 3 on 5.5.
Okay, 5.5 extra, is it this radios one?
Yeah.
Okay, so Radios for You has a fixed cost of $15,000. Okay, fixed cost of $15,000. And they find that their marginal cost follows the equation C prime of Q is equal to this quadratic function whose graph is seen on the right. Okay, and what do they ask us? Given the graph of C prime of Q to the right, represent the total variable cost of making 20 units graphically. Okay, the total variable cost. So we pay a fixed cost, and then we accumulate cost according to this rate, right? So what this says is when we're making 0 units, okay, we are accumulating costs at approximately $35 per unit, right? That's how we interpret this graph here. So how is it, if this is the rate of change of my costs, how is the total variable cost of making 20 units gonna appear in this picture? What do we think about, well, it's just this height? You agree or disagree? Is this the total variable cost of making 20 units? It's just, 15. No, what's not quite right about that? What is this graph measuring? Marginal cost. And what am I asking a question about? Total cost. What's the relationship between a rate of change and the total change? That's right. The total change from A to B is the integral of the rate of change from A to B. So if this is the rate of change, what do I need to do? To find the variable cost of making 20 units, I need to do integral from 0 to 20 of C prime of Q, right? dq. This will tell me the total change in costs from 0 to 20. Now how does that show up in this picture? What's the deal with, okay, this is the graph of C prime of Q. What does this mean in terms of our picture? So it sounds like you're saying it's the difference in height between this height and this height? Was that what you were saying? Do we agree with that? Well, that would definitely give us the difference in C prime from A to B. But we're interested in the total difference in C from A to B. Right?
Finding the area.
That's right. Integral of a function from 0 to 20 is just going to be whatever is the area under the curve from 0 to 20, okay? So that's this area right here. Okay? So that is how the integral shows up in the graph, right? Should always remember that the integral can be represented as the area under the function which we are integrating. Okay, so now let's not estimate C of 20, let's actually find it now that we have the tools to do so. How am I going to find out what C of 20 is? i.e., this is the cost of producing 20 radios, right? Has a very meaningful representation. So how do I figure out what C of 20 is, right? Gino? Well, we could count the boxes if we want, but we've even got the actual function itself, right? We can find this exactly, right? What relationship is shared between this integral and the function C of Q? How can I relate this somehow to the function C of Q? Yeah, well I have an integral of a derivative. What does the fundamental theorem say? If I do the integral from 0 to 20 of C prime of Q dq, what is this equal to by the fundamental theorem of calculus? Capital C with no prime of 20 minus capital C of 0. Right? And what is the question asking me for? Cost of producing 20 radios. How does that show up in this equation? Yeah, cost of producing 20 radios. is C of 20, right? So this is the number that we want, C of 20. Agree? Okay, so let's just rearrange this a little bit. I want to know what is C of 20. That's the cost of producing 20 radios. I know it's going to be equal to whatever C of 0 is, plus the integral from 0 to 20 of C prime of Q, dq. And this has a very, it looks complicated and there's a lot of working parts behind it, but what does this say in very simple terms? It tells me that the cost of producing 20 radios is the cost that it costs me to produce 0 radios plus the amount of costs which I accumulate by producing the first 20 radios. So now I just need to find out what these numbers are and get a numerical answer. So integral from 0 to 20 of C of Q. Okay, we can rewrite this. This is just C of 0 plus integral from 0 to 20 of 0.05 Q squared minus 2Q plus 35 dq. Let's focus on the integral first. How can I find out what this number is? Should I just plug in 20 right into this function? Sorry? What do I have to do first before I get plugging? Find the antiderivative, right? So I need a function whose derivative is the one seen here. So how do I do that? Well, let's start with the first piece. How do I find this antiderivative of this guy? Yeah, 0.05 is just a constant. It hangs out. What do? I increase the power by 1. I divide by the new power. Then I subtract 2Q squared over 2, right? Plus 35Q. And plus C, right? No, but why not plus C? It's a definite integral. I don't need a plus C. I just need a bar, right? Which goes from 0 to 20. And which one do I plug in first? 20. Okay, so what do I get? I get C of 0 plus whatever this number is, 0.05 times 20 cubed, all divided by 3, minus 2 times 20 squared over 2, plus 35 times 20. And I plug that in first, right? And now I subtract. But when I plug in 0, I just get 0. So it's minus 0, right? Okay, so do you agree that this number is my total costs to produce 20 radios? One thing's left out, though. What about this C of 0 here? What is that going to represent? That's right, fixed cost. This is the cost of producing 0 items. In other words, it's the cost to get my business up and running, which they say the fixed costs are $15,000. So my total answer for this would be $15,000 plus however much this number is. Which I'm not going to do because it's just calculator business, right? Plus however much that number is, and dollars. And I'm done. Okay, so what is this question about? Again, it's the same old story of they want to know what is the total change in costs. And what do they give us? They give us the rate of change of the costs. So we just use that fundamental theorem, we integrate, and we just need to use a little bit of thought when we get to this step, when we think about, well, okay, what do I really want? It wants us to find C of 20, right? The cost of producing 20 radios. So we need to isolate this quantity, which is why I added C of 0 over to the other side here, okay? And from there, we identified C of 0 as $15,000, and we knew how to find what that area is exactly, right? By using the fundamental theorem of calculus. I didn't have to count boxes or try to use geometry or any of that. I just found an antiderivative and I plugged in 20 and I plugged in 0. Yeah?
Why did you add like the minus 0 once you got it, like in the parentheses and brackets?
Okay, so you're talking about this minus 0.
Yes.
So what this statement says is take this function, plug in 20, which I did, and then minus when we plug in 0. But if I plug in 0 for q, I get 0 minus 0 plus 0. So that part just went away. But if it was, say, 1, maybe we're finding the increase in cost from 1 radio to 20 radios. Then we would have plugged in 20 and then done a minus sign and then plugged in 1. Does that answer your question completely? Yeah, no problem. Any other questions on this one? All right, then let's keep going. Does anyone have another topic that they want to discuss? Yeah, Clayton?
Could you do some optimization questions?
Optimization, absolutely. So that was chapter 4. So let me prime us by recalling what chapter 4 was about, right? Chapter 4 was about, okay, if I have a function, how do I figure out where is the maximum of that function and the minimum of that function, right? Which had something to do with these critical points, right? So critical points, when was I finding a critical point at a given x value? What was true about critical points? Well, if we have a critical point, it could be a minimum, or it could be a maximum, or it could be neither, right? But how do I actually find out where they are? Yeah, derivative, set it equal to 0, right? That was how we found where the critical points are. And then we check each one to see, is it a maximum, is it a minimum, using the first derivative test or the second derivative test, or yeah, one of those. Okay, so optimization was an application of this, okay, where, okay, we call it optimization because we're trying to optimize something. What might I want to optimize? Well, what would be optimal for me is maybe spending the minimum amount of money to get something done. Or what might be optimal to me would be maximizing my profits as a company, right? So this is about minimizing or maximizing a function, which is again about finding the derivative of that function, set it equal to 0, first derivative test, second derivative test, right? Okay, but the tricky thing about optimization problems is it's often given in terms of a 2-variable equation, okay? So for example, they might say we have a rectangle and we want to minimize the perimeter. Well, the perimeter of the rectangle is 2L plus 2W, right? 2 times the length of one side plus 2 times the length of another side. Right? But here's an equation which I have 2 variables. So how am I going to, quote unquote, take the derivative of this function, right? Well, what I have to do first is get an equation for one variable in terms of the other using outside info. So they'll say, I want you to minimize the perimeter of the rectangle, and then they'll give you some extra info, like subject to the constraint that the area of my rectangle should be 20, right? So we might have this extra constraint, which allows us, we end up with 2 equations with 2 variables. Okay, so we play our favorite game from algebra, and we just substitute, right? We solve for one of those variables in terms of the other, and we're going to put it back in. And then, what will we have? Then we'll have an equation with only one variable. And finding the maximum of that function is what we're after. So let's see an example of how this might go. I might have already done all of the optimization problems. Okay, well, how about this? Okay, you enclose a space by a river as an isosceles triangle. Using fencing on two sides with equal length. Wait, no. Why don't I say is this going to give me what I want? We've got a river, and then let's see, we have fencing, which would look maybe like this. Why don't I call it not an isosceles triangle, but a right triangle? Using a right triangle, using fencing on two sides so that we have a right angle here. Okay. Now the question is, if this length here is 100 feet, and you have what? Maybe like 400 feet of fencing. Then we can maximize the area enclosed. Okay, hopefully this will work out. We might have to modify this. In fact, why don't I modify it right now and just say we're gonna not use a right triangle. That's too precocious. We're gonna do a rectangle, which looks like the following. Sorry, I tried to get too fancy with it. Okay, so we're gonna use a rectangle. So we have fencing on three sides, right? Fencing on three sides. And I'm not gonna mention how long the riverside is. We just wanna maximize the amount of area which I keep in here if I have exactly 400 feet of fencing. So the question is, how should I distribute it? Should I have really long sides like this that go like that? Or should it be more square looking like this? Or should it be really long and wide in order to maximize the area which I enclose here? Okay, so we enclose a space by a river as a rectangle using fencing on three sides. Okay, so we have 400 total feet of fencing. We want to maximize the area enclosed. So we're going to follow the steps of the optimization problems one by one. The first step says get an equation for the function we want to minimize or maximize in two variables. Okay? So what is the function that I want to maximize? I want to max the area, right? Which is given by what? The length of this rectangle times the width. Where, let's call this one the width, and we'll call this the length, right? I want to maximize the area of this rectangle, right? Now, I need to have another equation involving L and W, okay, using outside info that is going to help me, okay, that is going to help me to eliminate one of L or W in this equation, right, so that I can then take its derivative. So what is my outside info that I'm going to use?
The fact that you have 400 feet of fencing.
Okay, I have 400 feet of fencing, right? How do I make that into an equation involving L and W?
400 equals 2L plus
400 equals 2L plus 2W. Do we all agree?
It would just be one L.
Yeah, I think just one L, right? Because we only use fencing on one of the L sides, right? The other side, we've got water. So we don't need to use it there. So we're going to do L plus 2W. Okay, so now we have two equations. One with L plus 2W equals 400, and one with A equals L times W. So I want to get rid of one of either L or W in the area equation, right? So how can I do that?
Solve for either variable.
Yeah, solve for either variable. I'm going to do L. So L equals 400 minus 2W, right? So then now we know what L is. If I take this, which is an expression involving W, and I replace it for L in the area function, then what do I get? I get the area is equal to 400 minus 2W times W, right? Okay, so this is the entire optimization process. We start with an equation in two variables, then we come up with something else from the outside info in order to get rid of one of them. So we went from an equation like L times W to an equation like 400 minus 2W times W. Now this is an equation that I know how to find the maximum of, right? In fact, it's emphatically clear that this is going to have a maximum, right? Because if we distribute, we get 400W minus 2W squared. Who can tell me immediately why is this function going to have a maximum?
Quadratic.
It's a quadratic opening downwards, right? If we have a quadratic opening downwards, all we have to do is find that one critical point. We know it's going to be a maximum, right? Okay, so let's finish this problem off. I need to find out what value of W maximizes this area, right? How do I do that? Set it equal to 0?
Finding the derivative first, right?
Find the derivative first. I think we should take the derivative and set it equal to 0. So A prime is going to be what? 400 minus 4W is equal to 0. So then that tells me that W is going to be, what is it going to be? Just 100, right? Okay. So I found a critical point of this function. Do I know for sure that it's a maximum?
In this case, we can just want to make sure.
Yeah, in this case we do because it's a quadratic. So I could say W equals 100, only critical point of a quadratic opening down. Therefore, it's the max. I could say that if I wanted to. Or I could use the first derivative test. If I use the first derivative test, what do? I put 100 on here, and now what am I supposed to do? Yeah, pick maybe like 101 and maybe 99. And I check whether it's positive or negative at those values. Well, I check 400 minus 4 times 101. I know that's going to be something less than 0, so I know it's going down. And then if I do 400 times minus 4 times 99, then I get something positive, which tells me I'm going up. So if I have a function which is going up, and then its derivative is 0, and then it's going down, you can surmise that in the middle we must have hit a maximum point, right? Okay, so this is how we do an optimization problem. Now, one thing I want to warn you about is that some of these problems will ask you something like, okay, they'll ask you something like, what is the maximum area? And in that case, it would not quite be correct to say the maximum area we can enclose is 100. The way we interpret this is that we will enclose the maximum area when the width is 100. From there, we need to notice that if the width is 100, then we know that the length is going to be 400 minus 200, which is 200. which tells me that our shape looks something like this. We've got 100 on the side, 200 on this side, and then we have our water, right? So if we want to find the actual maximum area, we have to actually plug in these numbers and find out what we get when we do the area of this thing, which would be 200 times 100. Okay, so finding W is to find the width which maximizes area. It is not necessarily the maximum area. We would have to plug it in to our area function. Okay, any questions on this optimization problem? Okay, sounds like people are done. So we can be done. If you have another question though, we can talk about it for a few more minutes. Otherwise, there's going to be a review on Tuesday. I hope to see you all there. I'll also record it though if you can't go, so that you can benefit from it still. Yep, have a good one. Yep. Hey.
About that email I sent you?
Okay.